All right. So thanks for the invitation. It's nice to be virtually back to the other side of Cambridge. In fact, we were just on the Harvard campus last weekend with my son, who was having lots of fun stamping in the puddles. I guess hopefully sometime we'll be able to come back and actually go in and see all of you. So I don't have that many slides here, maybe around 20, and the last few are kind of optional. So I'd like to encourage questions and discussion throughout because, you know, I'm going to be talking about some thorny and confusing issues, and I'm not going to go into all the details for everything. So if something bothers you or you want to disagree or anything, please speak up at any moment. And, you know, for fun, you know, turn on your video at least when you're going to ask your questions so that it feels a little more real. Okay. So this talk is based on a paper with Edgar Shigulian, who I think I saw was actually in the audience. You know, Edgar, feel free to chip in if I say anything wrong. It's about these three interesting topics of Euclidean gravity, global symmetries, and the black hole information problem. So let me start just with some review, familiar to most of you, hopefully. So this idea that there are no global symmetries in quantum gravity goes back a long way. I'm actually not sure if these are the first papers. So there's this paper by Banks and Dixon showing that in the string world sheet, any continuous global symmetry is promoted to a gauge symmetry from the space-time point of view. And then there were some speculations in these Euclidean wormhole papers of Giddings and Strominger. And then there was some further discussion in this paper from the Stanford group in '95. I somehow feel like the idea should be older than that. Maybe Kumran can comment, I don't know, or John or somebody.
Daniel definitely is older than this. It goes
That's
back.
That's what I thought, but I couldn't find the references.
Zeldovich, there are Zeldovich and collaborators who speak explicitly about this. There are also hints that Wheeler was thinking along these lines.
Yeah, I somehow feel like Wheeler knew this, but I couldn't find a paper where he said it. Yeah. Yeah, well, yeah, I'm curious if you want to send me an email or, yeah, because I feel like there should be definitely, yeah, this idea is older than these. Okay, so the rough idea is that, well, you can destroy a global symmetry charge by throwing it into a black hole. That's kind of the kindergarten idea. But that argument isn't so good because, well, why don't you just say that the black hole carries global charge, right? So you have to do something about that. And so far, to turn this idea into a real argument, it's either been necessary to restrict to continuous global symmetries, as in the arguments, which I guess were written down explicitly in this paper of Banks and Seiberg, although again, they were probably around before. Or you have to go to some more controlled situation, such as ADS-CFT, which is what Hiroshi and I did a few years ago. And then we were able to give an argument that works both for continuous and discrete global symmetries to exclude them. Requiring that, well, going to ADS-CFT, you know, in particular requires that the cosmological constant is negative, which is really too restrictive, right? I mean, we would like to think that this idea applies to the world that we live in. So then, you know, a proof based on ADS-CFT is not good enough. Okay, and then, you know, we knew that when we wrote the paper, but what can I say? You do what you can. On the other hand, there clearly needs to be some kind of assumption that's non-trivial because in low dimensions, there are actually theories of quantum gravity with global symmetries, and I'm going to review a few of them in a couple minutes. So we need some assumption which is strong enough to rule out these low dimensional theories. So you could, you know, just say, okay, well, I only want the conjecture to be true in 3+1 dimensions, but then that seems a little bit arbitrary. You know, what's so special about 3+1 or higher?
Sorry, before you go on, can I ask?
Yeah.
More generally, what do you expect that insights that we can get with lambda lower than 0? Which insights do you expect we can extrapolate to flat space, or more generally?
I don't think lambda less than 0 matters very much in the end. I mean, this is somewhat of a religious question, but I think that string theory is the only theory of quantum gravity. And it's kind of, you know, it has vacua with negative lambda, it has vacua with positive lambda. Well, I think it does. Maybe some of you don't. You know, the conjectures like this one I think of is really coming from short distance features of the theory. So they shouldn't be too dependent on being at negative lambda. You know, the advantage of negative lambda is that we have a non-perturbative formulation of the theory. So we can corner it a lot better than we can, you know, when we don't really know what's going on in more realistic vacua.
Okay. Okay.
So the goal of this talk is to propose what I view as a natural sufficient condition for excluding global symmetries in quantum gravity. The proposal is that in any theory of quantum gravity where black hole evaporation is a unitary process that's consistent with the entropy formula of Bekenstein and Hawking, or more generally the Wald formula, no global symmetries are possible. So in other words, the idea is that the unitary resolution of the black hole information problem is very closely tied to this idea of no global symmetries. If you don't have that, then there's no reason to expect that there are no global symmetries. Now, I'm not going to prove this. This is too general of a thing to prove. You know, we don't know enough about quantum gravity, but I'm going to give two kinds of evidence for this conjecture. So first, I'll show that so as we discussed, there are theories that have quantum gravity with global symmetries, but I'll show that none of those theories have black holes which evaporate unitarily, you know, consistent with the Bekenstein-Hawking formula. So somehow our conjecture allows these theories to have global symmetries. So that's argument number one. Argument number two is that we'll show that a version of my argument with Hirose can actually be applied to exclude global symmetries in any theory where not only is the radiation unitary, but the explanation of the entropy of the radiation goes via these recent calculations of Pennington, Almeri, Engelhardt, Merolf, and Maxfield, which are based on the quantum extremal surface formula. So at least if those are correct, then there are no global symmetries. So you can say like our proposal, establishing our proposal is kind of reduced to the assumption that the basic mechanism that works in these calculations is kind of the only way for black hole evaporation to be unitary and compatible with the Bekenstein-Hawking formula. And of course, I don't know that that's true. There could be some other way, and then this argument wouldn't necessarily apply. But at least to the extent that this is really the right idea, then as a consequence, it implies that there are no global symmetries.
Sorry, may I ask a stupid question?
Yeah, please. So Arthur first, then Jake.
Yes, so I'm confused whether this can maybe not be done. Sorry, you are basically. Sorry, my my sound is bad. Apologies. Let Jake go first. Let Jake go first. I have a problem with my sound here.
Okay, Jake.
Yeah. So we've talked about this before, but I'm just curious right now how you see this assumption as relating to theories of quantum gravity where there's no ensemble. Because you say that this is where you can make these arguments according to these lines, but these page curve arguments, but I'm just curious how much that relies on there not being an ensemble or there being an ensemble.
So I kind of never think there's an ensemble. So to me, it's a red herring.
Well, in these theories that have global symmetries, I'm guessing there would be an ensemble.
No, that's incorrect.
That's incorrect. Okay.
Yeah, there are theories with global symmetries that don't have an ensemble.
Okay.
Sorry, I fixed my problem now.
Okay.
So my question was about continuous global symmetries. So if I only care about continuous global symmetries, then it seems that all you want to claim is already done because you assume black hole evaporation, and then that's the process that being unitary.
Yeah. So as I mentioned, there's this argument in the Banks-Seiberg paper, which I would say is fairly satisfactory, excluding continuous global symmetries. This argument, though, essentially still relies on this assumption. So you can just say that, you can say that for continuous symmetries, this is already followed. This statement is proven by the argument of Banks and Seiberg. But it's not proven for discrete symmetries.
Okay, thank you.
And for discrete symmetries, you can prove it using ADS-CFT, which is, again, in ADS-CFT, we believe this assumption is true. So that's kind of consistent with our proposal. But this is more general than ADS-CFT. But yes, roughly speaking, I'm more or less satisfied with the argument in the continuous case.
I see. Okay, thank you.
Yeah. But somehow, it seems like it's not really getting at the main point, though, if it only works for continuous symmetries, right? Somehow there's some, unless somehow we think continuous symmetries are really fundamentally different from discrete symmetries, which I guess I don't believe.
Well, as a practitioner, I care mostly about the continuous case, so maybe.
Well, maybe that's good. Yeah, but I'm trying to understand why these things are true rather than, what their implications are. Yes.
Okay, thank you.
And I think the discrete one will be important. It is important for particle physics too, I should add. Maybe not as obviously so, but I think it still is. Yeah, any other questions, comments, concerns?
Could I just ask, sorry, follow up, what is the example of the theory, or are you going to tell us that has a global symmetry but no ensemble?
Yeah, we're going to talk about it.
We're going to talk about it. Okay, cool.
Yeah. Okay. Yeah, and in fact, we're going to talk about it now. So we're going to talk about simple quantum gravity theories with global symmetries. So in low space-time dimension, there are several examples of quantum gravity theories with global symmetries. So the most trivial examples are the world line and world sheet theories. So this is the particle world line, which it doesn't look like a gravity theory when you write it this way, but you can integrate in a dynamical 0+1 metric GTT. And then here it just looks like a 0+1 theory of gravity coupled to matter fields x mu. And similarly, this is the Polyakov action for the world sheet. And these both have Poincare symmetry, target space Poincare symmetry as a global symmetry, right? X mu prime is lambda mu nu x mu plus n mu. And this is an exact global symmetry of these theories. And these theories, at least in some sense, are quantum gravity in the sense they have a dynamical metric and a diffeomorphism invariance.
Daniel, can I ask there? So these theories, they have a metric as a dynamical degree of freedom, but they don't have black holes in any meaningful sense, right?
Bang.
So are there examples where you have global symmetries and a black hole?
Yes, there are. And we're going to get to those next. But I just want to start as simple as possible, right? So these are the kind of the most trivial examples. And so for these ones, the assumption that I said can't even be formulated because these theories just don't have black holes. So there's no sense in which our proposal would require these theories not to have global symmetries, which is good because they do have global symmetries.
Sorry, apologies. I promised I will shut up, but I would claim that the string world sheet can be read as having no global symmetries because you clearly can radiate a string. A string loop would be like a wormhole connecting to the world.
So here, so I should be clear here.
I understand that you're ruling that out. I read your paper that you are excluding that, but it seems to me somehow not quite fair. I don't know how to put it better to rule out that process, which violates global symmetry.
Well, so if you when I make this statement more carefully, so this is one of the details I wasn't going to get into right here, but when I quantize these theories, I do it using canonical quantization. So I start with these actions and I do what's in Dirac's textbook. And so if I do that, then the topology is fixed as a function of time. That's what comes out of canonical quantization. So that's, we can discuss about whether we like that or we don't like that. In fact, there's going to be a lot of discussion about that later in the talk. But for now, I'm just going to do what's in Dirac's book, and I'm not going to try to add on anything. In particular, if you do try to add splitting and joining interactions, say in the world line description, then this theory is no longer UV complete, right? You have to complete it into quantum field theory. And similarly, the string world sheet stops being UV complete. You have to complete it into something like string field theory. And so then we don't even quite know what we're talking about. So if we want to have a clear example where the theory is well defined, it's better to do canonical quantization and not try to sum over branching topologies.
So Daniel, for my question, you would say that these are an example of a theory. If you do what, as you said, and you just use standard canonical quantization, this is a theory that has no ensemble and global symmetries.
That's right. And in a minute, I'm going to give you an example that also has black holes and is an ensemble and has global symmetries.
I see. I guess in this context, I might have said that once you do sum over topologies, you might expect to see an ensemble.
Once you sum over topologies, what happens is the sum is diverging and the theory is
also
not
that. Yeah.
That's what happens.
Sure.
Yeah. Trust me, I'm going to discuss the Euclidean thing quite a bit later, okay? So people who love the Euclidean thing, I will discuss it. All right. So here's a more interesting example, which is Joukiev-Teitelbaum gravity coupled to conformal matter. So in Joukiev-Teitelbaum theory, you have a it's a two-dimensional theory. You have a dynamical metric G mu nu, you have a dynamical dilaton phi, and then you minimally couple to some matter CFT with, let's call the fields psi I, okay? And then there's also a topological term in the action, this phi naught, which is basically multiplying the Euler character. So this phi naught is a parameter in the action. So phi naught is a parameter, phi is a dynamical field. So this is a renormalizable theory of quantum gravity. So you can quantize it via canonical quantization. After you do that, you get a theory that's exactly soluble. So it's renormalizable, so it's well-defined, and it's solvable by a Weyl transformation to flat space. Essentially by going to conformal gauge. So anyone who's been around long enough is familiar with solving this kind of theory that way. And so in particular, if you have a global symmetry of this matter CFT, so for example, like if you have some, say this is n Dirac fermions, there's some UN flavor symmetry rotating them, that at least as long as there's no mixed anomaly, which there isn't in this case, then this global symmetry survives canonical quantization and becomes an exact global symmetry of the quantum theory. Okay. You can also think of time reversal as an exact global symmetry of this if you want to. So unlike in the previous two examples, this theory does have black hole solutions, which we're going to say a lot about a little bit later. But when we discuss them, we'll see that in the quantum theory, their entropy is infinite. Which is kind of similar. So I don't know if Andy is here, but it's similar to what happens in the CGHS and RST models. So when you think about the evaporation of black holes in these models, what you end up with is a theory with remnants, which are objects that have infinite entropy and finite energy. And so in particular, they don't obey the analog of the Bekenstein-Hawking formula for this model. So therefore, this theory is again allowed to have a global symmetry by our conjecture because the entropy is not given by the analog of the Bekenstein-Hawking formula. Yes.
Can I ask there, Daniel? So I guess this is related to the fact that you can also not form black holes in this theory. If you start in flat space with a bunch of particles, you're not going to form a black hole, right?
Well, yeah. So you wouldn't. This is roughly true. So I have a negative cosmological constant, so I wouldn't be in flat space anyways.
Sure, but still, right? Regardless.
Yeah, so the novel, right, so the feature of this theory, which is strange from the point of view of higher dimensional gravity, is that the vacuum has horizons, already has horizons. So, and that's kind of what allows you to sneak remnants. That's kind of what this theory is able to have remnants from low energy theory, is because of those horizons. There's a redshift factor, so you can put lots of information near the horizon in the vacuum, and you can get arbitrarily many states at arbitrarily low energies.
But this isn't like a Poincare horizon in higher dimensional ADS, right? Or
it actually is a bit like it is actually a bit like a Poincare horizon in higher dimensions. Yes. But the difference is that a Poincare horizon has the Bekenstein-Hawking formula would give it an infinite entropy because it's non-compact. Whereas here, the Bekenstein-Hawking entropy would be finite. That's the key difference. So there's a tension between this fact that they're classical remnants and the Bekenstein-Hawking formula.
Thanks.
Yeah, we'll discuss this black hole in more detail. So if that's all not obvious to you now, hopefully it'll become more clear later. So let me just mention one other, actually, yeah. So yeah, maybe now this will be the first of two places in this talk where I respond to the people who love the Euclidean path integral. So this is a bit of an aside, but let me say it. So in these examples, because of renormalizability, canonical quantization produces a well-defined quantum theory. And in particular, there's no averaging or anything funny like what Jake was asking about, because we're just doing what's in Dirac's book, we're going to get quantum mechanics. Okay. If you try to give a path integral formulation of these theories, you get a path integral where you sum over only globally hyperbolic topologies. So if you want to try to include more general topologies, such as what you would get by analytic continuation from Euclidean signature, so you can try it, but you have to add it by hand. It doesn't come out of Dirac's book. And if you do it, then there's no guarantee that what you get will either be well-defined or causal or even be quantum mechanics. Okay, and in fact, in Jakiv-Teitelbaum, let's say even with no matter CFT, this distinction is very clear. If you start with two asymptotic ADS boundaries and you do canonical quantization, the theory is exactly soluble and it's equal to the Liouville quantum mechanics. So this is a paper I wrote with Dan Jafferis back in 2018. Whereas if you try to, quote, quantize by summing over Euclidean topologies, you get an average over random Hamiltonians. And so you don't get quantum mechanics at all. And so that's why I put the quotes here. So I think in Euclidean gravity, I think everyone should put the quotes here, right? It's a thing you can do, but there's no guarantee that it'll have anything to do with quantum mechanics. And in fact, if you try to put back the conformal matter here, you try to introduce the matter fields, it's even worse. So if you introduce the matter fields and you try to do this Euclidean quantization, then even though the theory is renormalizable, it's still divergent because of pinching divergences in the moduli space. So it's even, despite its apparent renormalizability, it's actually not UV complete. And so then it's not even something we can really talk about by itself. We have to embed it into something else if we want it to be well-defined. So the point of view of this talk is going to be that the Euclidean gravity path integral is only compatible with quantum mechanics in theories where you're not trying to view the bulk path integral as the fundamental description. It's really something that you view as being emergent from some holographic UV completion. And time permitting, I'll try to justify that point of view more at the end of the talk. I have a few slides at the end where I give some more explanation of why Euclidean gravity is so different from canonical quantization. Okay. Any complaints about that little sermon? Hopefully, well, we'll see if we get to the end of the talk where I can explain it a little more. But for now, we're just going to adopt this point of view. So we'll only use Euclidean gravity in a holographic context. Okay. So let me just give one last example of a theory with global symmetry. This is mostly just to show that this is not purely a 1+1 dimensional phenomenon. So if you just take pure Einstein gravity in 2+1 dimensions, which I'll study with negative cosmological constant, so then we don't know whether this Euclidean, quote, quantization makes sense or not. There are a lot of people working on it now. Is it an average? Is it not an average? Does it exist? Is the sum over topologies divergent, and so on? But you can certainly make sense of it by doing canonical quantization, as was done in these papers. Then there's no funny business. You're guaranteed to get a sensible quantum mechanics. Now, the version which I want to study is the oriented version. So what that means is that we only consider spatial topologies, which are oriented manifolds. You can also do unoriented manifolds. But in the oriented case, then parity is a global symmetry. Okay, in the unoriented case where you included unoriented spatial topologies, then parity would be a gauge symmetry. So you may be familiar with this from the string worldsheet. There's something called worldsheet parity. And in the oriented string, it's a global symmetry, while in the unoriented string, it's a gauge symmetry. Now, this theory also has black hole solutions. So this is another example of a theory with black holes. But in fact, these black holes, again, have infinite entropy just in Jakiv-Teitelbaum. So that was shown in these two papers. There's two reasons. One is because the quantization of the moduli space leads to a continuous spectrum. And the other is that there's a divergent sum over topologies behind the horizon. So this theory, again, our proposal allows it to have a global symmetry. And it does.
Can I ask? Yes, so again, is it? I think it's also true in this example that you cannot form a black hole dynamically just by gravitational collapse. Is that right?
Yeah. Because there aren't any local degrees of freedom. That's correct. Yes.
But if I couple it to matter, I could have local degrees of freedom.
Yeah, but that destroys the renormalizability.
Okay.
Yeah, unfortunately, there's no, or fortunately, I don't know. In low dimensions, you can't, arrange a situation like in 3+1, where you can form a black hole out of nothing and watch it evaporate it and have complete control, which I think is not a coincidence. On the other hand, well, I was going to actually, maybe I'm going to discuss this now, actually. Yeah, actually, let me discuss this right now. Okay.
Maybe before you continue, one question.
Yes.
So where do BTC black holes fit into this?
Sorry, what? Well, those are the black holes I'm talking about here, BTC black holes.
But those have a finite entropy, right?
No.
Why not?
No. Because you can count the states. So that was what was done in these papers, right? So you count the number. So what the one-sided black holes look like in this theory are they're all quotients of ADS3, and they have some topology behind the horizon. So the pure BTZ doesn't work because that's actually a two-sided solution. So to get a one-sided solution, you have to do some quotient to introduce some topology. You can have some handles or something.
Okay.
Yeah, and there's just too many of those. There's far more than A/4G of those.
Daniel, just to be clear, what you're saying is that they have infinite entropy if you canonically quantize the theory. If this is arising as the low energy effective field theory of, I don't know, strings on ADS3 cross S3 cross T4.
Then it's not true. Then it's not. Yes, and that's a different theory, right? So what we're doing in these examples is we're taking the bulk theory completely seriously. Okay. And we can do that because of the normalizability, right? I mean, that's what I was going to say right here, is the reason we could unambiguously quantize these theories without any further input is because they were normalizable, right? Which is definitely not true of Einstein gravity in 3+1 dimensions. Was someone else asking something?
Yeah, Daniel, I had a question. Could you comment on C=1 Liouville quantum gravity? After all, there was a work recently of the Harvard group, I think, right? Well, there they effectively have non-trivial worldsheet topologies.
Well, I'd have to think about it. I mean, so also in Joukiew-Teitelbaum, you can include, you can, I mean, as I said on this slide, you can try to include other worldsheet topologies. I mean, I'm not saying it's never.
Yeah, so exactly. I want to understand these comments here. You're not claiming there's no way of understanding Euclidean quantum gravity in 2D with different worldsheet topologies. You're just saying that you require some UV definition of theory. And
that's right. I'm saying it's not complete by itself. Yes. At least, yeah. Or if it is, it's not quantum mechanics. So far, those have been kind of the two options. Either
yes, so I thought the work of Z Yin, I don't know who's on this call or he's on this thing or not. I thought he showed that in fact there was a consistent definition.
I think, okay, yeah, I think what he was doing was a bit more like holography. I'd have to think about it again.
Okay.
But I think that the fundamental description there is not the worldsheet. There's some, matrix model. Or
there's matrix model. I agree. It's a matrix.
Yeah. Model. So that I would say is more like holography, which is going to be, so that's the case. That's the thing I said in the last thing here, where you view this bulk path integral as a low energy effective description.
Okay. So that comment maybe we come back to at the end of the discussion, because I'm a bit confused about how that's holographic, but okay, we'll come back.
Yeah, I'm not sure. I'd have to think in detail about, I'm too young to have lived through the C=1 matrix model, so I can't immediately tell you in detail how it works, but I somehow feel it's more like this. Okay. It's also somewhat similar to the Solid-Schenker-Stanford thing, which again isn't, there it's kind of an average, I mean, there it's not quantum mechanics, but I don't know, maybe.
Well, yeah, I think this is different. I mean, I think the claim is it really is quantum mechanics.
Yeah, but then I think I'm going to say it's kind of holographic.
Okay. Yeah. Come back to that. Thank you.
Okay, so let me continue here with now trying to motivate this idea of holography a bit, right? So as I said, these weird low dimensional examples, I mean, they are weird. I'm not trying to sell them as how I think the world works. I think they're just important to think about. Okay, and well, the reason why I'm not trying to sell them as how the world works is because I don't believe in asymptotic safety. But I should say that you could hope for some kind of UV fixed point of Einstein gravity in 3+1 dimensions, right? We don't know that doesn't exist. I would say there's no evidence for it, and I maybe don't believe it. But if it existed, then I think it would allow global symmetries. So I think that these lower dimensional examples, what they're modeled for is, as in 3+1 dimensions, is asymptotic safety. And since I don't think that exists, I don't think they're a good model for 3+1 dimensions, but I don't actually know. Okay, and that's why I want to make this comment.
Could I actually ask you your take about this comment?
Yeah.
Why isn't the Weinberg-Witten theorem an argument against this possibility?
No, well, the Weinberg-Witten theorem, I think, is just kind of a confusion, right? I mean, they forgot the diffeomorphism. I mean, they're just kind of saying diffs have to be gauged, right? So when I mean, you could have tried to use the Weinberg-Witten theorem to attack these lower dimensional examples, but you just would have kind of missed the point, right? I mean, so it's true that they're not quantum field theories, right? Because there's a dynamical metric, but they're still local field theories. They just have diff symmetry.
I see.
So I mean, in some sense, they should be called quantum field theories. You know, if we rewrote the books, you know, fairly, we probably should call them quantum field theories, because why is the metric different from other fields?
I see.
But, you know, somehow quantum field theory has been defined as, you know, has local operators and energy momentum tensor and so on, and then these don't obey all those axioms. And that's kind of just the content of the Weinberg-Witten theorem, is once you have gravity, you don't obey all those axioms.
Sure. Okay.
Which is obvious to all of us.
Yeah, but it doesn't. You're saying you don't think it precludes this possibility?
Absolutely not.
Of having you. Yeah. Okay.
Definitely not.
So Daniel, can I elaborate a little bit on that? So would this be like a field theory with with local fields, but not stress energy tensor or something like this?
Yeah, yeah. I mean, it's just like an action like this, right? Like, I mean, you know, or just what we learned to do in the string weld sheet, right? Nobody, you know, there's some diff symmetry. You have to deal with it somehow by gauge fixing or something. But you know, you have a path integral over local fields. You just have to make sure you talk about gauge invariant observables, and everything is fine.
It's hard to imagine that such a thing would be local, though, right? Like,
but it is. Look, there it is, right? Like, look, local, right here. How can you not? Local, perfectly local. You know, it depends what you mean by local, of course. If local means, you know, you have operators labeled by points that commute space-like separation, that's not true. But that's my definition of local, is that the Lagrangian is local.
Okay. Yeah.
Maybe I can actually make one comment on that thought. These theories that you're talking about, these theories that are renormalizable and that just make sense by canonical quantization, don't really have like a Planck scale cutoff. The topology and geometry aren't fluctuating as wildly at the Planck scale as we think in more realistic theories of quantum gravity that have black holes and holographic principle, et cetera.
Well, I mean, these do have black holes, but yes, I agree.
They don't have.
It's true they don't have a cutoff. I mean, that's the point. We're not. That's why I said we're not viewing them as effective theories. We're taking the cutoff to 0.
Yeah.
Okay. So, and renormalizability allows us to do that. That's why we can say it's really a theory instead of some, you know, approximate thing that has to come from something else. Okay. So let's see, where was I? Ah, yes. Okay. So so instead, you know, so how do things? I think things work in 3+1 dimensions. So as we've been discussing, so all UV complete theories of quantum gravity in 3+1 or higher come from string theory, at least as far as I know. And those that we understand non-perturbatively are all holographic, in the sense that their fundamental description lives in a lower number of space-time dimensions at some asymptotic boundary. That's a bit vague, but that's the definition I'll adopt for holographic. Somehow this idea that there are no global symmetries is somehow really supposed to kind of only apply to these kind of theories. Okay. Now, our best understood example of a holographic theory is, you know, the ADS-CFT correspondence. And there's a very important feature of this correspondence, which we're going to use now for a while. And this is this thing called the quantum extremal surface formula. So some version of this was first proposed by Ru and Takinagi, and then it was developed over the ensuing 8 years into the final version by Engelhardt and Wall. So this used to be, you know, it used to be called the Ru-Takinagi formula, but at this point, you know, enough was developed beyond what Ru and Takinagi did that I think it's correct to call it the quantum extremal surface formula rather than putting names on it. It wouldn't be fair to call it the Engelhardt-Wall formula, because that wouldn't be fair to Ru and Takinagi, right? So either we could call it by this whole list of names, or we can just call it the quantum extremal surface formula, which is what I'm going to call it. And these days, I think it's what most people call it. So here's what the formula says. Okay, so this picture is ADS-CFT. Hopefully everyone knows about ADS-CFT. So the idea is you have a spatial subregion R, capital R, on the boundary, and you want to compute the von Neumann entropy of some CFT state rho. Okay, so of course you can compute it by computing minus trace of rho log rho. That's rho r log rho r. That's the definition of the von Neumann entropy. But the claim of the quantum extremal surface formula is that there's a bulk formula you can use to compute this microscopic von Neumann entropy. and here's the formula. So the idea is you look at the set of codimension 2 surfaces XR with the property. So this red line is a codimension 2 surface. You want the boundary of this surface to be equal to the boundary of R. So that's these 2 points here. That's sometimes said that XR is anchored on R. And you also want XR to be homologous to R in the sense that there's some spatial surface, little r of XR, in whose boundary is the union of big XR and big R, okay? So this sort of time slice here in the bulk in between the two is called this R of XR. Okay, then the rule is you look at the area of XR over 4G plus corrections that we won't worry about, and then you add to that the entropy, the bulk entropy of matter fields on this R of XR, and then you extremize that, okay? You look for an XR with extremizes that. And then if there's more than one, then you look for the one which minimizes the whole thing. Okay, so that's the quantum extremal surface formula. If you've literally never seen it before, that probably went by a little fast, but hopefully you've seen it before here in 2020. Any questions about this formula? It's kind of an amazing formula, right? I mean, the old Bekenstein-Hawking formula was a formula for coarse-grained entropy. This is a formula for von Neumann entropy, so it somehow is much stronger than just saying S equals A over 4G, even though it kind of looks like that. Okay, everyone's happy with the QES formula? Yeah, Miguel?
Can I ask a quick question? So yeah. Are there, this is supposed to be really, literally the exact, once I allow the bulk, if I was able to fully take into account the entropy of the field theory in the bulk side, this is supposed to be an exact formula for
it's supposed to be, I would say it's supposed to be true to all orders in G Newton. Okay. But there can be non-perturbative corrections which are not accurately computed by the right-hand side of this formula, yes. Okay. And that's actually important. Some of the applications crucially rely on the fact that the formula is approximate. So I just want to mention, I could give a whole talk about this, but I won't, that one important consequence of this formula is something called entanglement wedge reconstruction, which says that any operator in the bulk, which is in the domain of dependence of this little r of XR. So the domain of dependence of this little r of XR is this wedge here, which is called the entanglement wedge of R. I've labeled it WR. So this formula implies that any operator in the bulk, which is inside this entanglement wedge, can be reconstructed or represented in the CFT as an operator with support only on this capital R. So this conjecture has a long history. It goes back at least to 2010 earlier. The proof of it was in a paper by myself with Aaron Wall and Shidong in 2016, showing that this formula implies this statement. Okay. This is all part of the story about how ADS-CFT is a quantum error correcting code, but I'm not going to use that terminology in this talk today. Okay. Now I want to get to this issue of the page curve. So over the last decade, people have gradually realized that this quantum extremal surface formula can be used to compute the entropies of systems other than just a piece of a holographic CFT, right? Like here, this R is a piece of a holographic CFT, and we're computing some von Neumann entropy. But this formula is actually more general than that. And there are several ways of thinking about this. So already back in 2009, people understood in the context of tensor networks that that something like the QS formula is true quite generally. It's a statement about tensor networks. It was also shown basically in any quantum error correcting code. So including, I wrote a paper, and then there was this paper by a couple of Harvard students, Monica and Dan, that basically any quantum error correcting code has a version of the quantum extremal surface formula. And then in particular, if you have a holographic CFT that's coupled to an arbitrary non-gravitational system, it was emphasized in this paper of Hayden and Pennington that this coding interpretation tells you that you can apply the QES formula also to pieces of the non-gravitational system, which is talking to your CFT.
So can I ask, what is the parameter, like in, for instance, when I apply it to an arbitrary error correcting code, what is the analog of G Newton, like the parameter that controls?
Yeah. So in some cases it's exact. It kind of depends a little bit on the application. So if the code is an exact code, then the formula is exact. And if the code is an approximate code, then the formula is approximate with whatever sets the level of approximateness of the code. So in ADS-CFT, that's G Newton. Yeah.
Okay, thanks.
So that's one way of understanding the generality of this formula. Another way, which goes back even earlier to the work of Lifkowitz and Molsena, is that you can use this Euclidean replica method to give a rather general derivation of the QES formula, which doesn't rely on details of ADS-CFT. And it's kind of funny. So when they wrote their paper, they didn't talk about Rutakyanagi until the end of the paper. And their paper was about so-called generalized gravitational entropy. And at the time, I guess most of us thought it was a bit silly. Why were they being so general? The important thing is that they proved the Rutakyanagi formula. But now with the benefit of hindsight, as usual, Juan is a smart guy. And it was they were totally right to emphasize the general nature of the arguments and not to make use of any details of ADS in the way that the arguments worked. And then finally, so last year, based on the strength of these observations, these authors, had the guts to apply the QES formula to a reservoir coupled to a holographic CFT, and thus we're able to give a derivation of the page curve for certain evaporating black holes. And so since this is important for my argument against global symmetries, I'm going to give a bit of review of the page curve arguments. So to get ready, I'm going to do it in the context of Joukhiv-Teitelbaum just to be concrete. So let's first remember how black holes work in Joukhiv-Teitelbaum. So the basic idea is you have two, so you have the dilaton and the metric. So this is what the black hole solution looks like in kind of Schwarzschild coordinates. This is what the dilaton looks like. It grows linearly with R. So these coordinates here cover this kind of right wedge here in the green region. This is like the exterior in the Schwarzschild geometry. There's another wedge over here, and then there's a future interior and a past interior. This line here between the two dots is the ADS boundary. This line between the two dots is the other ADS boundary. So like with the Schwarzschild geometry, there are two asymptotic boundaries. These red lines kind of indicate the future of the theory in the sense of the region where the dynamics is well determined starting from the boundary conditions in the initial state. Beyond this, you have to make sort of arbitrary assumptions about what happens to the future of future infinity in the boundary theory. So the standard way to think about this is at least if you're trying to have a Hamiltonian formulation, you should just think about this green region. And up here in general, there will probably be some kind of singularities or something. So then, so this theory, it's 1 + 1 dimensional. So the Bekenstein-Hawking formula can't quite be correct, but what's true instead is that the entropy is 4 pi times the value of the dilaton at this bifurcate horizon point. Where when I say the value of dilaton, I mean both the dynamical dilaton plus this parameter phi naught that appeared multiplying the Euler character in the action. So this is more or less like the two-sided Reisner-Nordstrom black hole, basically. And we kind of throw out these regions up here for the same regions we throw them out in the Reisner-Nordstrom black hole. Okay, now what was realized in this paper of Ahmed, Netta, Don, and Henry is that you can realize a version of the information problem for this black hole by taking the right ADS boundary and coupling it to a reservoir, which consists of the same matter fields that you had in the bulk, but now propagating in flat space without a dynamical metric. So when you do that, so say you go to t = 0, you turn on a little bit of coupling. So when you turn on the coupling, it sends in a shock wave here and also here. That's just because you changed the Hamiltonian suddenly. And then after that, positive energy from the gravitational system leaks out into the radiation, and negative energy leaks back into the black hole, causing its mass to decrease with time. So since this theory is exactly soluble, you can compute the entropy of the reservoir system as a function of time, and you get some formula that looks like this. So basically, when t is 0, this has some value, and then you see it decreases with time. So sorry, I said this wrong. Increase. Sorry, when t is 0, this is 0, and then as t increases, this increases with time. Okay.
Sorry, Daniel, can I
Yeah.
ask the only reason why you can do this thing is precisely what you mentioned before, that these theories were normalizable. Like that you just take a gravitational system and then you just decide that at some point gravity is just not coupled anymore and you're just gonna couple it to a CFT, right? This is not something that we know how to do in higher
but you should
dimensions.
just think of this as a model, right? I mean, in higher dimensions, this area wouldn't be so clearly defined, but this gray area over here would still effectively be the Hawking radiation once it's far away from the black hole.
Right. So yeah, so this is what I'm asking. So this is something that when I try to read these papers always struck me as kind of odd, and I guess I just don't have the intuition how relevant it is. You're telling me not too relevant in any case.
I think the right way to think about this is that this theory, funny though it is, already has an information problem. So to the extent that we can make progress on the information problem here, that's exciting, even though we can quibble about the details of this, which aren't quite the way things work in higher dimensions.
No, I understand.
My personal feeling is that this kind of fact that we can couple the bath in a renormalizable way is not a crazy thing to assume, because for a real black hole, we do believe that, right? It's just, this gray area here is just the part of flat space that's far away from the black hole. It's just that calculations become harder to do than they are here.
Right.
In detail, but I think the mechanism should work in the same way.
Okay.
Yeah. So, okay, then the point is that this theory has an information problem if the initial temperature of the black hole is large compared to this parameter phi naught. So remember, this phi naught was this coefficient of the Euler character in the action, and that showed up in this analog of the Bekenstein-Hawking entropy. And you can see that if, well, at late times, this term is gone. And then, so then this term is just something that's proportional. So T1 is the temperature after this initial shell goes in. So T1 is kind of the initial temperature up here. T0 is the temperature prior to the shell going in. That's the definition of T0 and T1. T1 has to be bigger than T0 because you threw in some energy. So if the initial temperature is large compared to phi naught, then you can see this formula eventually becomes bigger than the coarse-grained entropy of the black holes, which is just this, okay? So then what we learn is that in this theory, the analog of the Bekenstein-Hawking formula is just wrong, okay? This is a formula for some entropy, but it's not the entropy of this black hole because, well, this theory is exactly soluble. We can exactly compute the entropy of the radiation and we get some, you know, it's on a global slice, the thing is pure, but, you know, so this has to be purified by whatever's over here, but therefore the entropy is whatever's over here has to be bigger than this, okay? You know, that's essentially the sense in which this theory has remnants. So this is the same thing that happened in the CGHS model, right? And it's just saying that this, you know, although you can write down this entropy formula, it's just wrong in this theory if we try to take this theory completely seriously by itself, okay? And so in particular, you know, since the entropy is formula is wrong, it's okay for this theory to have global symmetries, and it does, okay, if the matter theory does. All right. So, so far, that's all well and good. That's just the same as what happened in CGHS, RST. The real point is that it's much more interesting maybe to view instead of trying to take this theory too seriously by itself, we instead view it as a low energy effective theory, which is UV completed in some holographic description. So that's the ingredient that CGHS and RST didn't have back in the early 90s. If we do that, then we were allowed to use the QES formula and see what that tells us about the entropy. So before I do that, any questions so far? By the way, Miguel, I've kind of been assuming that the sort of the 45 plus 30 can be kind of interspersed since we're having lots of questions. Is that reasonable?
Yeah, it is.
Okay, all right, thank you. Just want to make sure I don't get in trouble here. Okay. And then okay, fine, you can use the QES formula. Okay, anyone can say it. In fact, people did think about it before, but the amazing discovery of last year was that they found a new candidate quantum extremal surface well, it has a very novel feature, which is that it's not near any classical extremal surface. So a classical extremal surface is one where you just extremize the area over 4G. Okay, a quantum extremal surface is one where you extremize this sum, okay? So the conventional wisdom until last year was that this term is big compared to this term, because this has a 1 over g in it and this doesn't, okay? So therefore, any extremization of the sum has to give you something which is close to an extremization of this term by itself, okay? That was what I thought, that was what many people thought. And if you think that, then you're definitely not able to compute the page curve, okay? So the great discovery was that if you are a little bit bold and you say, even though this term looks big and this term looks small, this term actually has a short distance singularity. The entropy of matter fields, if you bring, so 1 + 1 dimensions, the entropy of an interval, if you bring the points of the integral together, there's a logarithmic divergence. And you can boldly try to balance that logarithmic divergence against the 1 over g here, and try to find an extremal surface where both terms are equally important. And in the past, maybe that seemed wrong because, well, if you're balancing different orders of perturbation theory against each other, then why do you believe what you're doing? So that was maybe why that sounded suspicious before, but somehow here it's correct. And maybe if you ask me, I can say a little bit more about why I think it's correct, despite this issue of perturbation theory.
So can I ask, why do you think that's correct?
Essentially because it's justified by kinematics. So the higher order terms all go into this ... and this ... none of these are all local on this surface, so they don't have a logarithmic divergence. So the only logarithmic divergence comes from this term. So somehow it's the balance of this term against the variation of that is preserved even if you include the ...
Okay.
So you said, yeah, somehow the key point is all the corrections are local integrals on the surface.
So you wouldn't have an argument like this in Vasiliev or something like this?
In Vasiliev, I wouldn't even begin to know how to think about these questions. Yeah.
But some version of the quantum extremal surface formula should hold according to what you just said, right? Like,
I have no idea because I don't even know if that theory has an action formalism. Okay. Or if it's holographic. I mean, that's my level of confusion about Vasiliev is so severe that I don't. I mean, they say it has black holes, but in some gauge they don't look like black holes, and that's for people who are smarter than me to think about.
Fair enough.
Yeah. So okay. So then the point was that it's not obvious, but that there is a surface here at late time. So if we just zoom in the upper corner of the evaporating diagram that we had here, so we just zoom in up here. And since this argument is more general than Joukhiv-Teitelbaum, I put a space-like singularity here. There's a surface here, which turns out to be a quantum extremal surface. And basically the rule is you take the time of the boundary, you go back for what's called a scrambling time, then you go up a few Planck distances inside the horizon, and you can show that there's an extremal surface. And then once you convince yourself that this surface exists, then it's kind of clear it's going to do what you want, because as the black hole evaporates, this area of the horizon decreases with time as you go this way. So this area is the dominant thing, so this decreases. So it gives you a contribution to the von Neumann entropy, which decreases. So eventually, since the other one was increasing with time, eventually this is going to be the minimal one, and it's going to give you a curve that goes down. So for Joukhiv-Teitelbaum black hole, this is what the global picture of what's going on looks like. So you have here the surface has two components. It has a piece here and a piece down there. The entanglement wedge of the radiation system is at late times is the union of this yellow area on the radiation and this yellow region in the bulk, which is called an island. Okay. So people like to call these this region to the left of the new quantum extremal surface, they like to call it an island. So here you can see the island in the full JT picture. And once you include this quantum, so then there are two competing quantum extremal surfaces. There's the one where you include this island, and then the one where you don't, and the surface is just the empty set. And so then you're supposed to minimize, that's what the formula says. So you take the minimum over the two contributions, and then miraculously you find that as soon as you were going to be in a situation where this formula, which is the one we had before for the radiation, exceeds the Bekenstein-Hawking entropy, then the minimum switches over to this one, which doesn't exceed it. And so therefore you never have a contradiction with the Bekenstein-Hawking formula, and you get a page curve that looks consistent with unitarity. Okay, so that was the story of the papers of last year.
Daniel, can I ask a question about this?
Yeah.
Isn't it truly, this shouldn't be this smooth behavior? Shouldn't we have strong fluctuations, especially near the transition between these two?
Right. So right near the top, you have to be a little bit more careful because, you know, as in general with the first order transition, if you're trying to think about the finite n, right, or finite g, then there are other effects that you have to include that are subleading. So there are other effects that are subleading unless you're right near the top, and then they're not subleading and they kind of round out the top.
Okay, good.
But away from
incidentally, is that at all understood how that works? My understanding, which is probably far from complete, well, I know it's far from complete, is that process of rounding out is not at all calculated in any
there are
detail.
examples where it's computable. So like in Joukieff, I don't have time to get into it, but there's a toy model of this where you do Joukieff Teitelbaum with an end of the world brane instead of matter. And there it can actually be computed. In the West Coast paper of Pennington, Schenker, Stanford, and Yang, they actually compute it. They spend a lot of time studying exactly how that transition happens in that model. In more realistic situations, I don't think it's been computed in detail, though I think there were some papers from the Santa Barbara group saying some things.
Thank you.
I think Henry is saying, oh, Henry, hi, Henry is here. Okay, yeah, Henry is saying the same thing, yes.
Can I ask how important is really the time dependence in the calculation of the entropy? We're having an adiabatic picture here, right? Where you start like varying the temperature and then at each point we compute it as if it was time independent, or?
No. I mean, the time dependence is dealt with correctly in the calculation.
Right. So, no, I understand, but I'm asking what is.
Well, it depends what you want. I mean, if you want a page curve, you're asking about something that's time dependent, right? So there's going to have to be some time dependence.
Right, but I'm asking sometimes you can compute correct time dependence adiabatically, right? Like pretending that something is not time dependent. And then,
well, yeah, actually, that's kind of true here. So if you look at this formula, I didn't say it, but you can kind of like say this formula, this quantity T1 times the square root of this is actually the temperature at time t. So this formula is really just 6 pi squared phi b times t of t. And that's kind of the adiabatic approximation, which is kind of correct here because, well, there are various approximations that went into this calculation that I didn't discuss, but they, essentially they amount to making it adiabatic, if you like.
Thanks.
Okay, other questions? All right, I now want to get to global symmetries. So let me first recall the argument that Hiroshi and I had in ADS CFT against global symmetries. So our paper was 175 pages long, but here I'm just going to do it in a slide. And it actually is that simple. It's kind of unfortunate. I mean, I guess that's why we wrote the shorter paper, but yeah, the problem is there are always details people can complain about. So then we wanted to sort of anticipate all that. Maybe it was a mistake, I don't know. So here's the idea. So you can do it with either picture. Let's use the figure on the left. So this is a time slice of ADS. The idea is you imagine that you have some operator. So say you have a global symmetry, then you imagine you have some operator, this green one, which is charged under the global symmetry. If nothing is charged under the global symmetry, it's not a global symmetry. Okay. So then what we're going to do is we're going to look at the algebra of that operator with the symmetry. But we're going to be a little bit sneaky. So the symmetry, so say if we have a global symmetry in the bulk, it has to be a global symmetry in the boundary as well. But then by the locality of the boundary theory, we should be able to decompose the unitary that implements the symmetry on the boundary Hilbert space into a product of an operator that implements it in this region times an operator that implements it in this region and so on. And then possibly with some edge effects to deal with the fact that what happens right in between the regions is UV sensitive. So we may have to fix that up a little bit with some operator that has support only at the edges. So in the continuous case, this is just Noether's theorem, right? It's saying that the charge on the whole boundary is just the integral of the charge in each of these regions all added up, okay? But this version of it is true for discrete symmetries also. But then the point is that, this green operator is not in the entanglement wedge of any one of these boundary regions, right? So the entanglement wedge of R1 is this gray region. The entanglement wedge of R2 is this gray region and so on. And so therefore, by entanglement wedge reconstruction, this operator has to commute with all of the operators that are in here, okay? But well, if it commutes with all of these operators, then it has to commute with their product also, but then it can't be charged because being charged precisely means it doesn't commute with U of G, okay? And so that's the contradiction. is that you just can't have any charged operator in this yellow region. You can do the same contradiction where instead of using pieces of the boundary, you have multiple boundaries and then you have some wormhole connecting them, and there's the same contradiction. So any questions about that argument?
Well, yes, Daniel?
Yeah.
Can I ask a question? So, but this suggests that if I'm very close to the boundary, why isn't that, why do you then, so imagine I am close enough, so I'm within the gray regions.
Yeah. Well, then I can add more, then I can split it into smaller regions though. The problem is you have to pick your operator and then I get to pick my regions.
Ah, so the regions are not fixed in any
No, the regions,
way.
I can pick them to be whatever I want. So yeah, and the problem is whatever operator you pick, I'm going to be able to find regions where I can get this contradiction. Which is also, that's why I kind of drew the operator big, is because it could even not be like a field. It could be something that creates a black hole, but as long as whatever it creates has finite extent, I can always make the region small enough that I can have this problem.
Okay.
Okay, so that was our argument from 2018. Yeah, was there another question?
You used a lot the term splittability in the paper.
Yeah, so splittability went into this argument. So when I said by boundary locality, we can do this decomposition, that's where splittability appeared.
So what is that, I mean, since you don't emphasize it now, is that kind of obvious? Is this always holds? I mean, the CFT. So
well, I mean, that's okay. So this is getting into why the paper was 180 pages long. Morally, I think it's obviously true, but there can be theories where you have to fix them up a little bit to make it true. Essentially, if they're topological degrees of freedom in the boundary CFT, splittability won't quite be true in general.
My question
but it's kind of, what I'll say is it's kind of always true enough that we can make this argument.
My question is kind of more simple. I can start with a gravity theory, which I think is well defined on the gravity side. So I have no knowledge of the CFT. I kind of define the CFT as being the dual of the gravity theory. And then it's totally obvious to me because it may be a very strange theory, one that you never encountered anywhere else.
But I think it should obey the axioms of conformal field theory. That's what I'm assuming. So if you want to say that the boundary theory does not obey the axioms of quantum field theory, I have nothing to say to you. I mean, it may be, then it's not, I wouldn't call it ADS CFT. But I would say this follows from very general properties of quantum field theory. Like if you talk to algebraic quantum field theorists, they'll definitely tell you that this is true. Okay. The only reason that we kind of didn't just say that, we didn't just say it's true because Hogg says it's true, is because Hogg doesn't understand topological field theory. And if he did, he would understand that it's not quite true. But the sense in which it's not true in topological field theories or theories with topological degrees of freedom is kind of irrelevant for this argument.
I have a question.
Can I ask a follow-up? Can I ask a follow-up to Arthur's question? Sorry.
Yeah.
So if the CFT is a logarithmic CFT, does a suitable version of the splittability property hold there?
I would guess yes, but I'd have to think about it. Certainly, this is most natural to think about in theories with the discrete spectrum, but I would guess it should be true more generally. Yes, I mean it's the only thing that causes trouble here is that you can have surface operators that are topological. So as long as you don't have that, which I would say in general in logarithmic CFT in general you usually don't, I guess, or I don't even know if there are examples where you do. Then I would say that this should still be true. It's just a statement that, I mean, because essentially the thing that implies this is just that the symmetry sends every local operator at any point to another local operator at the same point. That's a very strong restriction on this U. And certainly like in the lattice context, you can just prove that it implies that it has this decomposition.
Yeah, no, I believe the lattice case, definitely.
Yeah.
The question is whether every interesting theory can be got by a lattice regularization.
Right. So that's, and so we thought about that. I mean, there's a section in our paper that's like 40 pages long about this kind of questions.
Okay.
In the end, I would say And none of the issues which arise cause me to have concerns about this argument. Let me put it that way.
Okay.
Okay.
I have a question, Daniel.
Yeah.
So what? It seems to me though that there's this issue. How do I know that the green operator isn't in the entanglement wedge of the support of U edge?
Because U edge lives only at these points, right? So it's a measure zero. It's localized in a measure zero region in the boundary, so its entanglement wedge is empty.
I mean, but U edge isn't a separate product of all of those, right? I mean,
it may not be, yeah. I mean, I guess that's part of why we introduced the example on the right, is because then there's no U edge. Since the regions are all separate components of the boundary. So maybe that's one way to see that this can't be a deep issue. But usually when we talk about entanglement wedge reconstruction of a region, we allow arbitrarily complicated operators on the region. So in particular, we allow operators that mix the different points together. And that does, I mean, that can make the entanglement wedge bigger than the union of them separately. I mean, in fact, it does usually. But I don't think it can make it big enough to include this if it's measure zero on the boundary. We could try to compute it using the formula, but if you think about, I mean, here we're just talking about the vacuum, right? So if we try to apply the quantum extremal surface formula to these, say, I mean, it doesn't even make sense if, you know, because it's written in terms of codimension 2 and so on. So we'd have to take it as a limit of the regions getting small. But I think basically the point is, if you have a bunch of intervals and you think about their entanglement wedge, and the limit that you take all the intervals together to zero size, you're somehow never in the region where the phase transition likes to include a big piece of the interior. If you think about it geometrically, it's kind of clear that that's going to be true, because it's always better to close the surfaces the small way instead of the big way. Does that make sense?
Yeah, I think I can see that. Yeah.
Yeah.
Sorry again. So if the dual is an ensemble of CFTs, does the argument still go through?
No, but yeah, but I'm not talking about that. Yeah, I mean, so again, I don't believe in theories like that. So,
okay.
Yeah.
Good, thank you.
Yeah. Okay, so let me continue. So to extend this beyond ADS-CFT, we need a few assumptions. So these are going to be a little bit vague because we're trying to be general, but hopefully you'll see the sense in which these assumptions are needed. So let's just say S is some quantum gravity system which has black hole solutions and whose semi-classical description lives in d dimensions. And then let R be a reservoir system, which consists of weakly interacting quantum fields on RD or possibly some subset of RD. So then I'm going to assume the following things. So I'll assume that I can couple R and S together such that if you have a pure state black hole in S, it produces Hawking radiation, which is then gradually transferred to R. So this certainly was realized in the example we discussed before, where R was the non-gravitational bath and S was the holographic CFT. We'll further assume, and this is the key assumption, that we can compute the fine-grained entropy of S and also subregions of R by using the quantum extremal surface formula. Okay, so this is the main non-trivial assumption, I would say, assuming the QES formula is correct. And then finally, we'll assume that if there are any global symmetries, then then the coupling between R and S preserves those. And moreover, that their action can be extended to be local on R. So that also is natural, essentially, in the case of a black hole evaporating, right? It's sort of saying that whatever global symmetry is, it acts locally on the Hawking radiation, you know, when it's far away from the black hole, which I think makes quite a bit of sense. Okay, and so roughly speaking, you should just think of S as the black hole and R as its Hawking radiation. And if you're happy to just think about that loosely, that's fine. I just tried to formalize it a little bit here. Okay, and so then we can just get the same. The idea is now that by allowing the black hole to evaporate enough that where it's old enough that the entanglement wedge of the radiation has an island in the black hole interior, then we can just realize the same contradiction. Okay, so here's the setup again. So here's our quantum extremal surface. So let's first think about this red line here. Okay, this is the microscopic description of what's going on. This dot is the region S, which describes quantum gravity, the quantum gravity system. it's a time slice of that. This red line is a time slice of the radiation system, okay? Now what we do is we split the radiation system up into pieces, R1, R2, R3, and so on, such that the entanglement wedge of the whole radiation includes the island. That's what we get by making the black hole old. But the entanglement wedge of any individual piece of the radiation does not contain the island. So like say for this piece R1, this shaded gray region is just the entanglement wedge of region 1. This gray diamond is the entanglement wedge of region 2, and so on. And then this gray diamond here is the entanglement wedge of the quantum gravity system S, all right? So this is color-coded in the same way as the picture we had here. So these gray things here become these gray things here. This yellow region here becomes the yellow region here, and the green dot here is the operator that's supposedly charged under the global symmetry. But then we just have the same contradiction, right? So the global symmetry has to act locally on the radiation in S, so it has to be a product of something unitary on S, some unitary on R, some R1, some unitary on R2, and so on, possibly up to these kind of edge configurations again. But then by entanglement wedge reconstruction, well, none of these pieces here can reach this green operator because it's not in the entanglement wedge of R1, it's not in the entanglement wedge of R2 or R3 or S, okay? And so therefore, actually the operator had to be neutral and was just the same contradiction again. Let me also just mention, so you can try to quantify this by computing some observable in the bulk, which where the observable depends on the fact that the charge in the island is not 0. So and then you can see that since this argument says that it has to be 0, there's some mismatch between what the quantum extremal surface formula would tell you, and what entanglement wedge reconstruction would tell you, and what the bulk would tell you. And so that was the approach of this paper. 2 recent papers, both interesting, that came out just a couple of weeks ago. One by Yiming Chen and Henry Lin, and the other by Poshen, Luca, and Jen Bean. Okay, any questions about this?
So I have a general question about the setup. How do you expect this? It's possible to improve any of these approaches to be more quantitative, like to tell us something about how quickly is the global charge being dispersed?
Well, yes, that's kind of what's done, and that's kind of what's done in these papers here. Yes. It's a little bit subtle. There's a subtlety here, which is that, so I phrased this as a proof by contradiction. So if it's a proof by contradiction, there's no point computing anything else once you have the contradiction. It just doesn't exist, okay? But what you would want, what would be nice, and you know, these papers, it's not totally clear how they're thinking about it. Henry is here, so maybe he can comment. The way you want to think about it, which I think we would all agree, is you imagine something called an approximate global symmetry, and then you try to use this argument to put a bound on how good that symmetry can be. So I think some steps in that direction are taken in these papers. Right now, it's not so clear how to translate those, say, into questions about, you know, coefficients of symmetry violating operators and the effective action and so on, which is maybe what you really want.
Yeah.
But it's at least potentially possible to do that.
Do you also see a connection with weak gravity conjecture in that case?
Not immediately. So yeah, so to me, weak gravity is not actually, it's better to me. I don't like to think about weak gravity as a lower bound on a gauge coupling. I instead like to think about it as an upper bound on the mass of charged particles. So you somehow need to get weak gravity. Well, first of all, you need to be talking about a gauge symmetry. And secondly, then you need to, it's really a generalization of the completeness hypothesis, I would say, not a generalization of no global symmetries. Because it's not a statement about global symmetries, it's a statement about gauge symmetries. And if you, and it's really a statement that there exist these objects that have some charge, right? So saying objects exist is somehow a little bit different from saying that some symmetry is violated somehow, right? Because weak gravity doesn't say anything is violated, it just says you need to have these charged objects.
But I mean, the fact that you can take G to 0 and say something, you cannot.
Well, yeah, I guess, but you have to think about what happens to the charged objects when you do that. I guess that's right. So if you somehow assume that I guess the way you get into trouble is you have to assume that the objects have finite mass in the limit that G goes to 0. Right. Yeah. Okay. In the paper with Hirose, we had 3 conjectures. This was one conjecture. The second one was the completeness hypothesis. That one can be turned into some weak gravity-ish inequality, which we did, and maybe at some point we'll write a paper about. But it's not quite this argument. It's more that argument that leads to that. Okay. There may be some way to think about it this way too. It's just not obvious to me because this argument didn't make any assumptions about the masses of charges, and that's clearly it's going to have to go into weak gravity.
Okay. Do you see any difference when applying this argument instead to a discrete symmetry, like trying to constrain the order of a discrete symmetry? Would that make it easier somehow?
No, I mean, the point of this argument is it's the same for continuous or discrete symmetries. Yeah. I mean, if the symmetry is continuous, as Arthur, I think, said in the beginning, you can just use the Banks-Seiberg argument. So this is a bit overkill. But I feel like this also is somehow a deeper argument. I mean, it kind of shows you, I mean, there's some inputs that's the same because you assume the Bekenstein-Hawking formula and so on. But here we had to use a little bit more. We really had to use that the evaporation was unitary.
Yeah, if I could just comment on that, I would say that the Banks-Seiberg argument, for example, can't tell you much about situations where there's an island, but there's no evaporating black hole. So there are situations where there's a non-trivial quantum extremal surface, and then these arguments would tell you that charge conservation or whatever is violated, but Banks and Seiberg wouldn't tell you anything.
Who is talking? Is that Henry?
Yeah, this is Henry. Yeah.
Hi, Henry. I recognize your voice. Yeah.
What is an example of such a system? When can this happen? Do you have like an island but no black hole, no horizon?
Well, there can be horizons, but perhaps the most non-trivial would be in these cosmological contexts. So like context where you have a closed universe, which is just entangled with some CFT, and then you have an island inside the closed universe. And these arguments would tell you that you can't have global symmetries, or that, I mean, they can tell you a little bit more. They can tell you exactly how they're violated quantitatively in these closed universes, let's say. Whereas Banks and Seiberg couldn't really, I mean, the closed universe doesn't interact with the CFT in any way. So
right. Maybe that's the best thing to say, actually, is that Banks-Seiberg doesn't give you any way to quantify the approximate case, whereas this seems like it should.
Right. I guess I would say that I agree with your sort of philosophy that of what you summarized about at least our paper. I would say that yeah, we're assuming sort of that you have an effective Lagrangian with the exact global symmetry, and then finding that there's a violation anyways. If you have terms that you add to the effective Lagrangian, which explicitly break the violations, you'll have an effect on top of what we're talking about. But in some cases, it looks like the effects that we're talking about here are sort of the dominant effects, even if you have relatively, I mean, even if you have terms in the effective Lagrangian, which are only polynomially suppressed by G Newton, for example.
Right, Henry, but what we really want to do now is we want to take your effect and show that it feeds back into the effective action and creates violations, right?
For sure, yeah. Yes. Yeah, that seems a little tricky. I mean, maybe in principle it's possible, but
yeah, it's not obvious how to do that, I agree. But well, I'm feeling bad about the time here. So I had these comments about the Euclidean path integral, but I don't know, maybe we should stop. I don't want to keep everyone basically.
Yeah, I think so the whole thing can go on for like until 1/2 or so, basically.
This is like less than 5 minutes maybe, but I mean like 3 or 4 minutes.
But that's we have 7 or so, so up to you.
Okay. I don't know how you think about it. I see. Okay, yeah. I can say it. I mean, okay, if you don't mind, I'm happy to say. These are just some comments. There's nothing hard really here, but maybe just to address some of the issues that came up earlier. Okay, I'll try to go fast. So I just want to return to this question of the validity of Euclidean quantum gravity. So we saw that it. So as I mentioned, the argument of Lukowitz and Maldacena shows that the QES formula follows from Euclidean quantum gravity. That was their paper back in 2013. In these theories like the JT theory, where you just take the canonical quantization completely seriously, Euclidean quantum gravity gives the wrong answer for the entropy. So you can use it. It tells you the QES formula, but the QES formula is just not right. On the other hand, it does give us the right answer if we think about the bulk theory as an effective theory, which is the low energy limit of some holographic theory. And so in fact, Edgar and I promoted this to a general conjecture, which is that the Euclidean path integral in gravity in a gravity theory with the quantum mechanical UV completion, correctly computes the entropy only if that UV completion is holographic. It shouldn't just be some local normalizable theory in bulk. And then moreover, the entropies that it computes are the entropies of that holographic description, not some effective entropies of the low energy theory. So in other words, Euclidean gravity and holography are in some sense equivalent. So I just want to motivate this for a couple slides and then I'll be done. So let me first remind you that in quantum field theory, the path integral representation of the thermal trace always lives in a Euclidean spacetime where the topology is a circle times some spatial manifold. Okay, that's essentially obvious, right? You just insert complete sets of states into this trace and you get a circle, which is not contracting. And this is true for canonically quantized gravity as well. So any gravity path partition function computed within canonical quantization has to live on S1 times sigma for some sigma, possibly with a sum over the appropriate sigma. So there's a Euclidean gravity path integral you can just derive from canonical quantization, but it's only going to include topologies like this, okay? Now, there's a simple argument that I think goes back to Hawking that geometries like S1 times sigma are never going to give you an entropy, which is of order 1 over g, at least as long as you think that the time translation symmetry around the circle is unbroken. And the reason is pretty simple. It's just that the Euclidean action has to be proportional to beta in any such situation. So if you try to compute the entropy from the partition function at leading order in 1 over g, well, you get 1 minus beta d beta on I, but if I is linear, is just proportional to beta, this is 0. So there is no canonical quantization can't lead to an entropy, which is of order 1 over g. Okay. Now, the standard fix to this is you say, okay, well, let's just forget about canonical quantization. Who cares? Let's just include Euclidean geometries, which are not of this form of a circle times sigma. And instead, we can only require that the boundary topology is a circle times something. So, and then we sum over all of these. Okay, so this is an example where on the left, this is kind of the Hawking-Page transition. So we have a circle which is non-contracted through all the bulk. At the end here, some other cycle contracts, say in the sigma. So this is like the thermal ADS saddle point in the usual language. And then this is like the black hole saddle point. And so if we allow that thermal circle to contract in the bulk, well, that kills the canonical interpretation. But on the other hand, we get the right answer. We get S equals A over 4G, as explained by Gibbons and Hawking. Okay. So great, this seems like, okay, so this is some way of getting the black hole entropy. Okay, on the other hand, why are we allowed to include this geometry on the right, right? This geometry would not have been included in the partition function derived from canonical quantization. Well, so in holographic theories, I think the answer is sort of morally clear at least, which is that since the microscopic description really lives at that asymptotic boundary, that's where the true thermal circle lives. So away from that boundary, there's no particular region to prevent the S1 from contracting. And in fact, if you don't, at least in ADS CFT, you get the wrong answer for the high temperature density of states in the dual CFT, right? Like the extensive entropy of, high temperature entropy of the CFT comes from this contribution and not from this one. This is still mysterious though, because, when you think, and this has bothered me for years, there seem to be two kinds of people who are bothered by this and people who aren't, and it's very hard to convert them from one camp to the other, but let me try. So how can a low energy effective theory, just the Einstein-Hilbert action, have access to such deep non-perturbative information about quantum gravity, right? That's normally not how effective field theory works. You can't know about the details of the UV just by knowing the low energy effective action, okay? So this has driven me crazy. I've always thought of Euclidean gravity as witchcraft because of this. There's some rules that you can't derive, but they give you the right answer for some mysterious reason. And it's still mysterious. I can't give a complete answer to how it knows the answer, but at least in ADS CFT, I can say a little bit more, which is that from the boundary point of view, you often have high temperature, low temperature duality that relates geometries in the bulk where the thermal circle contracts to geometries where it doesn't, right? So in ADS3 CFT2, this is modular invariance of the boundary theory on a torus. So that was in 1+1, and then in higher dimensions, Edgar has written many papers about this, showing that something like it is true in any dimension. Now, we do expect that gravitational effective field theory should be able to compute the partition function in a spacetime where the circle doesn't contract, such as the thermal ADS, right? Like this saddle point, we can compute it in the low energy theory just by doing a trace over, thermal gravitons in ADS. Well, at least if we believe this, that there's this high temperature, low temperature duality, then that also means that we can reliably compute the high temperature density of states by just pushing that calculation through the duality. And so that gives some reason why the low energy theory has to know this. So from this point of view, you can think about what Euclidean gravity is doing is it's just kind of putting back the minimal amount of information about the UV that you need to restore low temperature, high temperature duality on the boundary, which kind of removes this distinct treatment of spatial and temporal circles that came out of canonical quantization. You know, that doesn't mean you have to include it, right? I mean, this is UV information, so it's an assumption. But if we assume that the UV theory has this low temperature, high temperature duality, which from a holographic point of view is very natural, then it seems like it would be crazy not to include these more general topologies in the bulk picture. And apparently this sort of minimal amount of UV information, which goes into doing the Euclidean path integral, is also sufficient to determine the page curve and to forbid global symmetry. So a lot of good stuff already comes from this very minimal data about the UV. Okay, and I think I'll stop there. Thank you.